Gravity. It's the one thing keeping you from floating right out of your chair. We feel it, literally every single second of our lives, but what is it really? That simple question has taken us on this incredible journey from just watching an apple fall to questioning the very fabric of spacetime. And believe me, it's still packed with mysteries. All right, so here's how we're going to tackle this. First up, a fun little challenge. How do you explain gravity to an alien? Then we'll jump into Newton's big idea, this invisible pull. After that, we'll see how Einstein just blew that whole concept up by talking about warped spacetime. And we'll finish up with the modern mysteries, the stuff that still keeps physicists up at night. So to really wrap our heads around gravity, let's start with a little thought experiment. I want you to imagine a visitor shows up from a universe where gravity just isn't a thing. They get physics, sure, but they have never ever felt that constant pull we take for granted. Where would you even begin? How do you describe it? Okay, so this alien, let's say they've got a body, they understand space and time, all the basics. But in their world, things just float. Nothing falls, nothing gets pulled together. So, what's the simplest, most bottom line explanation you could possibly give them?
It all boils down to something incredibly simple. In our universe, things with mass are attracted to each other. That's the rule. You put two objects out in the middle of empty space, away from everything else, and they will, ever so slowly but absolutely for sure, start to drift together. That's it. That's the heart of it all.
And get this pull applies to everything with mass. But, and this is the really important part, distance matters a lot. Just think about it like this. You might hear astrologers talking about how the constellation Pisces influenced you when you were born. But in terms of pure physical gravity, the doctor standing right there in the room had way, way more of a gravitational pull on you. Why? Simply because they were so much closer.
So, what is this mass we keep talking about? Well, it's pretty much just the amount of stuff an object is made of. But here's the cool part. Mass does two jobs. It creates that gravitational pull, right? But it also gives an object inertia. That's its resistance to being pushed around. It's kind of like that feeling when you just do not want to get out of bed. It takes a real push to get you moving. That's inertia.
Okay, so this fundamental idea, mass and attraction, this is what led to the very first grand theory of gravity. And for more than 200 years, Isaac Newton's explanation was basically the final word on the subject. He painted this picture of a perfect clockwork universe, all run by this mysterious invisible force. Now, here's a really mind-bending idea that came from Newton. He realized this pull is always a two-way street. So when you drop a pen, yeah, the Earth is pulling the pen down, but, and here's the wild part, the pen is also pulling the entire planet Earth up to meet it. Of course, the effect is just impossibly small. We're talking about the Earth moving up by about 9 trillionths the width of one proton. But the force is absolutely there. It's real. So Newton's whole brilliant theory really breaks down into 4 simple rules. First, there's an invisible force between any two things that have mass. Second, the more mass you've got, the stronger the force. Third, the farther apart things are, the weaker the force gets. And finally, number 4, this force is what makes things accelerate. It's why an apple falls, and it's also why the moon stays locked in orbit around the Earth. Simple, elegant, and it just worked.
And for centuries, Newton's laws were perfect. I mean, you could predict everything from the path of a cannonball to the orbit of a planet. It was rock solid. But as our tools got more and more precise, a few tiny little cracks started to show up in his perfect theory. And these cracks hinted that gravity wasn't just a force. It was something much, much weirder.
I mean, just look at this timeline. You can really see how long Newton's ideas were the king of physics. For centuries, that was it. Case closed. But then, a problem popped up. A problem with Mercury. The planet closest to the sun just wasn't following the rules. Its orbit was wobbling, just a tiny bit, but in a way that Newton's math just could not explain. And this Mercury problem started forcing people to ask some really deep questions. Like, according to Newton, if the sun just vanished, poof, we'd feel the gravitational effect disappear instantly, faster than light could travel from the sun to us. That just felt wrong, impossible even. And that nagging wobble in Mercury's orbit wouldn't go away. It took someone completely new, a fresh mind, to ask a truly radical question. What if gravity isn't a force at all? And this is where Albert Einstein enters the story and just changes the game completely. He said, forget the invisible pull. Gravity isn't a force acting through space.
Instead, he said that huge objects, like the sun, are literally bending and warping the very fabric of space-time itself. So planets aren't being pulled, they're just moving in a straight line through a universe that's curved. Imagine a marble rolling around the edge of a bowling ball placed on a trampoline. The marble is just trying to go straight, but the curve in the fabric forces it into an orbit. What we feel as gravity is just the shape of reality.
Okay, I know, visualizing a bent, four-dimensional universe is, well, it's pretty much impossible for our brains. So let's simplify. Picture an ant on a flat sheet of paper. To that ant, the shortest path from A to B is a straight line. But for us, looking down from our 3D world, we can do something the ant can't even imagine. We can just fold the paper and bring those 2 points right together. Einstein's genius was realizing that mass does something like that to our universe. It changes the very rules of geometry. And this isn't just some wacky, abstract theory. This is real. We can actually measure it. Because gravity doesn't just warp space, it warps time. Time literally ticks by slower where gravity is stronger. So a super accurate clock in London, which is closer to the center of the Earth, will run just a tiny bit slower, about 5.6 microseconds a year slower, than an identical clock way up in the mountains of Boulder, Colorado. In fact, the GPS in your phone has to correct for this effect, or it would be off by miles every single day.
So Einstein's theory was this massive triumph. It nailed Mercury's weird orbit, it predicted things like black holes and gravitational waves that we're only just now properly observing. But you know how science works. In solving those old Newtonian mysteries, it ripped open a whole new can of worms, a set of even deeper, even stranger questions.
Right, so back in the 1930s, there was this brilliant, famously grumpy cosmologist named Fritz Zwicky, and he's looking at these huge clusters of galaxies, and he realizes something is seriously wrong. They're spinning way, way too fast. Based on all the stars and gas he could see, they should be flinging themselves apart. The gravity just wasn't strong enough. It was like there was some invisible, massive something holding them all together with its extra gravity. He called it dark matter. And that's not the only headache. There's another huge problem when we try to look at the world of these super, super small, the quantum world. See, all the other fundamental forces have a little messenger particle that carries the force. Electromagnetism has the photon, the strong force has the gluon, and so on. But gravity, we've got a theory that it should have one, a particle called the graviton, but we've never, ever found it. It's the biggest missing piece in the puzzle. And that brings us right up to today, to right now, where gravity is still the weird one, the great outlier of physics. It's shockingly, unbelievably weak compared to the other forces. It absolutely refuses to play nicely with quantum mechanics. And it seems to be screaming at us that there are enormous gaps in how we understand the entire universe. So why is gravity so ridiculously weak? I mean, a tiny fridge magnet can beat the gravitational pull of the entire Earth. Well, one of the wildest theories out there suggests maybe it isn't weak at all. Maybe gravity is just as strong as all the other forces, but we only feel a tiny fraction of it because most of it is leaking away into extra hidden dimensions of space that we can't see or touch, kind of like that ant on the paper who has no idea there's a whole up and down world just beyond its reach. You know, Einstein's idea of warped spacetime has an ultimate extreme conclusion. What happens if you take it all the way? Well, if you pack enough stuff, enough mass into a tiny, tiny space, you can bend spacetime so much that it basically breaks. It tears a hole in reality. You create a region where the escape velocity is faster than the speed of light itself, a place where nothing, not even light, can get out. You get a black hole. And just to give you a sense of the insane density we're talking about, think about this. If you could somehow take the entire mass of our planet, I mean everything, every rock, every ocean, all 8 billion of us, and squeeze it all down until it became a black hole, it would be smaller than a dime. It would have a diameter of just under 9 millimeters. The entire Earth crushed down to the size of a marble. And really, that's the thought I want to leave you with. Our quest to understand gravity has taken us from a simple invisible pull to the very shape of reality itself. It's forced us to completely rethink everything we thought we knew. And if our entire world, everything we've ever known, could be conceptually crushed into something you could hold in your hand, it just makes you stop and wonder, right? What other huge, profound secrets about the nature of reality are we still missing? What's waiting for us just around the corner?